Hello, everybody. I'm Sergiu Carpov. I'm a senior cryptographer at Arcium, where we are doing MPC. In this talk, I'll speak about recent work of mine in the domain of fast bootstrapping schemes like TFHE, and particularly on mapping Boolean circuits to functional bootstrapping. What is the context and motivation of this work is that the usual way to execute a Boolean circuit using a functional bootstrapping scheme is to execute each circuit gate using a single bootstrapping. And this is not the best approach because as we shall see after, we can do it better by grouping several gates into a single bootstrapping. So this will be the goal of this work, is to map the gates of a Boolean circuit to large functional bootstrapping. This will reduce the number of bootstrappings used in executing this circuit, and as a side effect, it's a good side effect, it will increase the execution performance of the execution. Another important thing is to do this mapping automatically, so that there's no or little human interaction in the process. And also we'll try to use the full functional bootstrapping properties in particular from the TFHE scheme. So what is fully homomorphic encryption? As the majority of you know about it, fully homomorphic encryption is an encryption technique which allows to perform computations on encrypted data. The ciphertexts are noisy in these schemes by construction, and we need a noise reduction procedure in order to reduce the noise in the ciphertext and to be able to continue the computations. And this procedure is called bootstrapping. There are two main categories of FHE schemes, the BGE, BFE, CKS, which have a slow bootstrapping, but they are efficient at message packing. So we'll be able to do some kind of SEMD operations, the same instruction, but on a lot of data. And the second category is FHE or TFHE schemes, where they provide a fast bootstrapping, but you'll only be able to bootstrap one message at a time. And another interesting thing in these schemes is that besides reducing the noise in the ciphertext, you will be able to compute an arbitrary function over the encrypted message. So, and we call this procedure functional bootstrapping. So you reduce the noise, and also you compute, you can make a nonlinear projection from the input message to the output message. So there are two main schemes. Historically, the first fast bootstrapping scheme was proposed by Dukas Michancho. It was a few scheme. They focused on two input and NAND gates because a NAND gate is a functionally complete set of gates. You can implement any Boolean circuit using only NAND gates. This work was extended to multi-input or larger Boolean gates in a subsequent work. And the second scheme, which was proposed in 2016, was TFHE. The implementation is really fast. You only need 10 milliseconds per gate. The number changed in the number changed each year because the hardware performance increases. So now I think it's 5 milliseconds per gate. And you are able to execute any two input gates and also a three input multiplexer gate. And besides this logic gate oriented implementation, you can the TFHE scheme support binary decision diagrams and deterministic automata, which allows to implement functionalities in a different way as binary gates. And a subsequent work, the TFHE scheme was extended to support multi-output gates and at the price of one bootstrapping. So you only do one functional bootstrapping, but you are able to compute evaluate plenty of functions or several functions on the same input, which is in some cases is I mean, interesting. It's interesting. So what is a functional bootstrapping? Functional bootstrapping is simply yeah, I'm looking here at schematic here, and also I'm also only interested in what happens in a plain text space, and I ignore all the details, technical details about noise propagation, how it's implemented, etc. So functional bootstrapping, it can evaluate any function on f on the space ZP. The computational cost of a functional bootstrapping depends on this plain text space size P, because in order to be able to support a large plain text space, you must have a more precise bootstrapping. So the bootstrapping the parameters of corresponding scheme will increase, and you will be less performant. So on the right, you have an illustration of an input message space, which is inside the circle, and outside the circle you have an output of a functional bootstrapping. So here you see a plain text space with 10 messages. The input has a value from 0 to 9, and the output will be the evaluation of a function f on these values. Schematically, the steps in a functional bootstrapping schemes are easy to understand. You have an input LW encryption of a message n, and this encryption is transformed into a GSW encryption of x to the power of m. So we use GSW encryption of a secret key S in order to do this transformation. And the x to the power, the powers of x represent a group in the polynomial ring of GSW. So this accumulator x to the power m is multiplied with a test polynomial. Test polynomial is a polynomial which encodes a function we want to evaluate f as some tricks when you encode the function f. But the result is that when you multiply x to the power of m by this test polynomial, it will rotate the test polynomial in such a way that the constant coefficient of this polynomial will be exactly f of m. So after this operation, you will obtain a RLW encryption where the constant coefficient is exactly fm. And finally, you extract from this ring LW sample the constant coefficient, and you obtain the LW output. And you can repeat this procedure ad infinitum, because the LW sample has a smaller noise, and you can do it for any multiplicative depth. What are other interesting facts we'll use in this talk about functional bootstrapping is functional bootstrapping supports not only power of two message spaces, but you can support any message space, any plain text space, like Z10, etc. The drawback when plain text space is not a power 2, is that it slightly increases the noise propagations because P does not divide N, where N is a polynomial ring size. So this creates, as you can see, the illustrations of the boundaries between each message. You have cells, which cell represent an unit in the polynomial ring. And on the boundaries, you are not exactly on the boundaries between two values, but yeah, and these boundary values are lost. That's why the multiplication is worse in this case. Another interesting fixes are the negacyclic functional bootstrapping. The most negacyclic they comes from the fact that the most efficient schemes use ring W samples, which are in a negacyclic polynomial ring, and particularly this one. Particularly modulo x to the power n plus 2 plus 1. And when projected to the functional bootstrapping plain text space, this corresponds to evaluating functional bootstrapping where the input message space is 2 times larger than the output message space. It's 2p, z2p. But the limitation is that the function you can evaluate cannot be must verify this relation. So if you look into the illustration, we have message space Z5, and when you look to on the function evaluation side, the outer of a circle, you'll see that for 0 and 5 message 0 and 5, for example, the output of message 5 will be the minus function evaluated in point 0, etc. for all the other points. So this is the drawback of negacyclic functional bootstrapping, but it allows to increase for free the plain text space. So what is a multi-input functional bootstrapping? As we have seen earlier, bootstrapping allows to take as input an encrypted message in ZP. And if you want to extend this bootstrapping to several inputs, we can do it like this. We decompose the function, the multi-input function f, small f, into big F, into a composition of 2 functions. The first one is a linear function which combines LW samples into one value. This linear combination can be is cheap and is done by plain text, ciphertext multiplications and ciphertext additions. It doesn't increase the noise of the input messages much. And a second step will be second function will be a nonlinear part, which takes as inputs these linearly projected inputs, and will evaluate a single one input functional bootstrapping on it. So in this way, we are able to evaluate any input functions. Let's talk about more the linear combination side. So linear combination is valid for given function multi-input function f if it can unambiguously distinguish its image. So more formally, if we have any two input points x and x prime, such that the function input function f has different values in these 2 points, then this implies that the linear combination also must have different values in these 2 points. So in this way, if the linear combination function project the points to a different value, the functional bootstrapping will be able to separate them during the bootstrapping procedure. Another important thing is the linear combination size. So the size of a linear combination is the smallest plain text space which is needed to evaluate this linear combination. So for example, if you take the linear combination to x plus 3y, the image of this combination will be 0 to 3, 5 for where x and y are Booleans. So for example, if x and y are zeros, you'll have 0. If x is 1 and y is 0, you'll have 2, etc. And the image size of this linear combination will be Z6 because it corresponds to the maximum of the image minus the minimum of the image plus 1. So if you have a functional bootstrapping or a plain text space Z6, you'll be able to evaluate this to do a bootstrapping of this linear combination. Linear combination is optimal if for function f if it's a valid, and also it has a minimal image size. A small image size means we need a smaller plain text space, and thus the functional bootstrapping will be cheaper. This problem is hard because exact methods are intractable for large n, for large number of inputs, and usually in the literature we use heuristics to solve this problem. So here are some examples of linear combination. For example, if you have symmetric Boolean functions, you will take a linear combination like this, like the sum of inputs, because it will allow to evaluate any symmetric Boolean function. And a symmetric Boolean function is a function where the output depends only on the number of set inputs and not on their position. And there are plenty of such functions like an input and or XOR gates, majority gates, etc. The advantages of this linear combination is the image size is linear in the number of inputs n. However, in order to be able to evaluate arbitrary Boolean functions, you will need this kind of binary composition functions, so, where you map the inputs, the input vector x to a value from 0 to the spaces, actually to the space z 2 to the power of n. This linear combination is functionally complete because you can, using it, you can evaluate any Boolean function. However, exponential image size results in expensive functional bootstrapping cost. And in practice, we want to have some kind of intermediary combinations between these two extremes. In case we are not able to map all the Boolean gates to symmetric functions. So let's go to the Boolean circuit mapping to functional bootstrapping to this work. So what we want is to partition a Boolean circuit, an input Boolean circuit, so that each obtained partition can be executed by exactly one functional bootstrapping. As an input argument, as input parameter, we have functional bootstrapping precision, or the maximal load plain text space size. And also, besides obtaining these partitions, we must output a valid linear combination, which allows to evaluate the logic functionality of this partition or subcircuit. The objectives of this work will be to minimize the number of functional bootstrappings in the mapped circuits, and ideally this will also minimize the execution time. because less bootstrappings, and less execution time. So some in the literature there several many works, several works which treat the same problem. Two main categories can be distinguished. The first one is related works which use the know-how from the logic synthesis domain in order to do this mapping. So there are plenty of works, some cited here. The advantage of these works is that the functional bootstrapping mapping is performed automatically without human interaction. However, some works start by partitioning the circuit into cones or sub-circuits, and they try to find a linear combination for multi-input functionality, or for a partition with multiple inputs, which is time-consuming. Other works try to restrict the accepted Boolean function in the mapping to generic and to symmetric Boolean functions, which allows to apply directly logic synthesis tools. And also almost all the works use only a power of two plain text spaces, which reduces significantly the solution space. Another line of works is manual mapping, where the authors try to hand optimize the applications to functional bootstrapping, and mainly to cryptographic algorithms like Trivium, Cravium, or iOS. They use, because it's manual hand optimized versions, they use efficiency tricks from the underlying scheme, FHE scheme, like neglect cyclic functions, like large plain text space, like tricks how to pack intermediary results together, etc., etc. The drawbacks of this work is that they are difficult and time-consuming, and also, as we shall see later, not always the best solution is found. So, yeah. Now, let's talk about the fast heuristic. The heuristic proposed we takes as input a Boolean circuit with two input gates. We know that any Boolean circuit can be mapped to a equivalent circuit which uses only two input gates, and also takes a maximal plaintext space size of a function bootstrapping precision. And the main idea of our heuristics is to traverse the circuit gates in a topological order once, and for each gate we'll try to construct a linear combination from the linear combinations of its two inputs. So we'll track for each circuit gate, we'll track its linear combination, which allows to we'll track a very linear combination, which allows to evaluate this node. And if obtained linear combination for a gate is too larger than the FB functional bootstrapping precision, we will bootstrap an input of this gate and redo a process. So like this, we will be able to find the valid linear combinations of a size smaller than the constraint set by the input plaintext precision. So let's look into an example. Suppose we have this simple circuit with three inputs, two gates, and an output. The first step of heuristic is to assign truth and value tables to each input. A truth table is the evaluation of a node of a circuit gate. Is evaluation of a logic function of this node, And the value table or multi-value table is the evaluation of a linear combination function of this node. So having these two tables, we are able to track a function bootstrapping test vector needed to evaluate this gate. So, for example, in case of inputs, this function bootstrapping is simple because it's the identity function will map 0 to 0 and 1 to 1. We'll see later that for more complex functions, this allows to save some computations. So let's take the first node to visit will be the vector node here. And the first step will be to compute that it's the truth table of this node. And in order to do this, the heuristic will do a Cartesian product of the truth tables of node inputs. And here you can see the Cartesian product as the pairs, as the columns of these two vectors. So 0, 0, 0, 1, 1, 0, 1, 1. And once we obtain this Cartesian product pairs, we will apply the logic function of the node to these pairs, in this case XOR, and we will obtain the truth table of the node. So 0 XOR 0 is 0, 0 XOR 1 is 1, etc., etc. We have this obtain this truth table of an XOR node. We can do the same thing for multivariate tables. So we start by computing the Cartesian product of gate input value tables. But here we don't have a functionality. We must combine these value tables using a linear combination. So what we can do, we'll find the optimal linear combination coefficients. In this case, they are 1, 1. And we will combine the Cartesian product of input value tables using this linear combination. So, for example, 1 times 0 plus 1 times 0 is 0. The last one is 1 times 1 plus 1 times 1 is 2. So we will obtain a value table for this node, which is valid because, as you can see, this evaluation this value table can distinguish all the elements of a truth table, and we will keep track of this of linear combination for each node. For example, for XOR we have A plus B, and A plus B allows to evaluate any to have something which evaluates this function. Sorry, it's the wrong thing. So now if you continue, we do the same for the next node, which is the AND gate. We do the Cartesian product of AND gate input truth tables like 0, 1, 1, 0 and 0, 1. We obtain these Cartesian product pairs. We apply the AND functionality and these pairs, and we obtain the truth table of the AND gate. And do the same thing for value table. We do the Cartesian product. We find the optimal linear combination coefficients, and you obtain the value table of AND gate. And this value table will be is able to distinguish all the elements of AND gate truth table. This value table corresponds to a linear combination which we track for each node. In this case, it's A plus B because it's one time input XOR, which has a linear combination A plus B, plus 2 times input C of AND, which is that's why you have 2C. So yeah, the evaluation of A plus B plus 2C on every possible values of A by C you'll obtain this value table of a node. Now, once we have computed these value tables and truth tables for node n, we must output it, and we cannot output it as a linear combination because it has values from 0 to 4, and we want a Boolean output. So in order to do it, we'll introduce a bootstrapping, functional bootstrapping, which takes as the input the linear combination of a node of an n node, a plus b plus 2c, and a test vector, which is built starting from the truth and the value table of a node n, and it corresponds it's the index, the element of a position, of a corresponding position from the value table will have a corresponding value from the truth table. So for example, in the test vector, the first value will be equal to 0 because it's the value table is 0. The second value from the test vector will be 0 also because it has the position is given by the value table value. And if you do with this, etc., you'll obtain the test vector for this functional bootstrapping. Now, suppose that we beside the node n, beside being an output, this node n is used subsequently in the circuit for our logic gates. And in this case, we won't use the linear combination for the node n, but we want to use the output of functional bootstrapping for this node because we already computed the functional bootstrap. We already computed the bootstrap. We already bootstrapped this node. So why use a large value on truth table? If we can use an identity truth table, because the n node is bootstrapped and it has 0, 1 values. So when we do it, we switch from the linear combination. We replace the linear combination of a node functionality by a functional bootstrapping, by corresponding functional bootstrapping. We reset to the truth and value tables to identity, and you continue the circuit traversal with these new truth and value tables. And we do it for all the nodes of a circuit. So these are the main three ideas which are used in the heuristic. So why the heuristic is fast? Because the circuit nodes are visited only once, and the linear combinations are built incrementally. So at each time we only try to build a two-coefficient linear combination. So how these linear combinations are built? We use exhaustive search. So we test all the possible linear combinations, like alpha x plus beta y, and we keep only the smallest valid one. We limit the search space of coefficient alpha beta values to this, and we can prove that this doesn't restrict so although the optimal value will always be found. This exhaustive search is faster than integer linear programming in our tests. And also we can include some specific test vector validity in case of negacyclic rings. As in negacyclic rings, the size of a functional bootstrapping will be 2p, and the functional bootstrap might verify the negacyclic relation. So this is easily integrated in this step. Let me give an example. So for example, you have a truth table of a node n, which is 0, 0, 0, 1, etc. the second column is the Cartesian product of value tables from node and node inputs A plus B and C. We have all pairs, and for example, we take a we have an example. For example, we take three possibilities for linear combination coefficient alpha beta. If you take, for example, 1 1, we can apply this linear combination to the Cartesian product and we obtain these values 0 1 1 2 1 2 2 2 3. But however, observe that this multi-value output is not valid. This linear combination is not valid because the truth table 1 has value 2, and also truth table 0 has also the same value 2. So we won't be able to distinguish the 0 from the 1 using this linear combination. So that's why this linear combination is invalid. Let's take for example, two other linear combinations like 2 1 and 1 2. We can do the same things. We obtain these value tables, these two values tables. The linear combination size is different because here, in the case of 2 1, we have a plain text space of 6. We need 6 distinct values in order for this linear combination. However, in the last one, we need only 5 different values. So the linear combination size is smaller in this case. Our algorithm will choose the second option because it's smaller and potentially it will pack better the gates in this linear combination. Now, for example, let's look at the test vector, which are built from these value tables and the corresponding truth tables of again n. In this case, in the first case, we have 0 0 1 1 0 0 because the truth table 1 corresponds to 3 in the value table. So the third position of a test vector will be 1 and the other will be 0. The same thing happens here. The truth table 1 has position 3 in the test vector and other zeros. However, observe that if you use the negacyclic property for the test vector, these two cases reduce to the same test vector, to 0 0 1 1, because after 4 positions, we can apply the negacyclic property and we have the same test vector in both cases. So so finally, both these solutions are valid because both they have the smallest functional bootstrapping size in case of negacyclic functional bootstrapping. So some details about the implementation. The implementation is available on GitHub. You can either copy the link or scan the QR code. It takes a belief file as input and it outputs a FPS mapping. It uses a concrete compiler to estimate the functional bootstrapping costs. It is patched to support non-power of 2 plain text spaces. And also we do a randomized equivalence check between input and mapped circuits to be sure that the map circuit has the same functionality as the input circuit. For example, for the AES circuit, on the left-hand side, we have projected the number of bootstraps and the evaluation cost in red as a function of functional bootstrapping size of the solution obtained by our heuristic. So in case of 2 is the input circuit, which uses one gate, one functional bootstrapping. And the best solution is obtained for functional bootstrapping size of 6. We have 45 less bootstrappings, and the execution time decreases by 70%. 70%, yeah. And all of these are compared to the naive approach of when functional bootstrapping size is 2. A thing we have observed is that the number of bootstrapping does not decrease monotonically with the increase of functional bootstrapping size. And this is due to the fact that our heuristic is greedy and it is counterintuitive, but when the functional bootstrapping size increases, the nodes, the gates will be bootstrapped later in the process of execution. So this will potentially result in more bootstrap gates. You can imagine this by imagine you have a gate which has a huge fan out. So if you bootstrap this gate, you'll save subsequent bootstrappings. But if you don't bootstrap this gate because your functional bootstrapping allows to execute it like a linear combination, then you'll pay the price because subsequently you will need to bootstrap each fan out of this gate. So this is why the drawback of the greediness of our heuristic. We have also tested on the suite of combinational benchmark from BPFL, where 10 arithmetic and 10 random for control circuits. We keep the solution of the smallest execution cost for FP sizes from 2 to 15. On average, we obtained a 37% decrease in execution cost and almost 60% less bootstrapping count. And another observation from our benchmarks, from our result, is the solution almost always use the functional bootstrapping sizes less than 8, which leads us to a conclusion that the increase in the cost of individual bootstrapping for larger sizes, it cannot be counteracted by the decrease of number of bootstrappings in the mapped circuit. Another interesting bench we did is on Trivium and Trivium stream ciphers, which are both stream ciphers on both 80 and 128 bits of security. One iteration of this of Trivium and Trivium is illustrated here. The underlying things are the addition from Trivium. And in our test, we have implemented 2 versions. This is only the only manual input from a human, and we did this in order to thwart the heuristic greediness. And what we did, we interchanged we grouped together the XORs in the last 3 instructions. So we do the ends in first place, and after this we do all the 3 or 4 XORings. And we compared this result of our heuristic to the hand-optimized versions from the literature. So for Trivium, the best solution is obtained for functional bootstrapping size 6. It uses only 4 bootstrappings, which is a minimal one because it's the number of outputs of a circuit. It's it's faster than the literature case of P equals to 3 and 2 times faster than the input circuit. And compared to a literature, we obtain a slightly better solution because we obtain the same number of bootstrappings as in the literature. The literature is the point red dot. We obtain 8 bootstrappings, but in our case, 8 bootstrapping for smaller plain text space 3, which translates to a small evaluation cost, slightly small evaluation cost. In case of Trivium, the results are more interesting because, as before, for P equals 6, the best solution was obtained for functional bootstrapping size 6, which it uses 5 bootstrappings. However, if we limit to compare to the literature, we limit ourselves to functional bootstrapping up to or equal to 4, and our heuristics outputs a map circuit with only 8 bootstraps, starting from p equals 3. And at the same time, a literate hand-optimized version has 10 bootstraps. So the increase when you compare the evaluation cost of our heuristic output with a literature, we have almost 30% decrease in evaluation cost. Here's an example how you can use a heuristic to map a trivium, one iteration of trivium to functional bootstrapping. Yeah, you only call the map circuit, you give the B file of the Boolean circuit you want to map, you give a size, the functional bootstrapping size, and it will output some aggregates of mapped solution. For this case, it uses 8 bootstraps, like presented earlier. And it will output also this kind of formatted text, which gives you the linear combinations of the corresponding bootstraps of a map circuit. So in case of functional bootstrapping 3, we have 8 bootstraps. And what is interesting that almost the same, the difference between trivium and trivium is only on the size of several test vector, which increases by 1, and the linear combinations, which have one more value. And also observe that the mapped circuit heavily uses negative cyclic property because all the test vector has a size larger than 3. The smallest one is 4 and the largest one is 6. So the last one use the negative cyclic property at the maximum level, which is helpful because it allows to decrease the number of bootstraps. So final notes. The conclusion, the incremental grade merge idea is simple, but it yields good results. The negacyclic and non-powerful plaintext spaces are powerful in order to obtain less bootstrappings, faster circuits, faster executions. And also, as a matter of fact, up to the large functional bootstrapping size were not used by our heuristics. Maybe if if you can better map the circuit to functional bootstrapping and further reduce the number of bootstrappings for the same size, it will be interesting to have functional bootstrapping of larger sizes. And in perspective, we want to implement an executor for circuits mapped to the FPS in order to have to obtain real execution numbers and not only estimations. It will be helpful to integrate the multi-output functional bootstrapping from the literature in order to furthermore reduce the number of bootstraps by merging together functional bootstrapping which has the same input values. And also another interesting perspective is to apply these techniques to arithmetic Garbel circuits, which from the optimization point of view or Boolean circuit mapping point of view is very similar to TFHE functional bootstrapping mapping. Thank you. I'll be happy to answer all your questions either here or if you look on GitHub, and I'm happy to answer any question.